Hey there, it's Shannon Mapchick-Myers, and today we'll be looking at section 8.2.1, which covers homogeneous linear systems and focusing on eigenvalues and eigenvectors. So this particular section introduces 8.2, and then the subsection deals with real non-repeated eigenvalues. So here we go. If capital X, now all of these capital letters are matrices or column vectors, is equal to K1, K2, all the way down to K sub n times e to the lambda t equal to capital K e to the lambda t is to be a solution of the homogeneous linear system capital X prime equals capital A times X, then capital X prime equal to K lambda e to the lambda t. So the system becomes, so we've got capital K lambda e to the lambda t is equal to capital A times K, again capital K, these are all matrices except for the exponential, e to the lambda t. So now we can divide out an e to the lambda t because that is non-zero. So we'd have capital K times lambda would equal to A times K. And then getting these on the same side, we would have the zero vector on the left and A times K minus K times lambda. Now, the zero vector will then be equal to A minus lambda times I. And this is because, just a little note, that the K vector is equal to IN times K, the identity vector. So that is where we get the result. And then that, of course, is times the vector K. And so now the matrix equation, A minus lambda times I, so lambda is a scalar, times K equal to the zero vector, is equivalent to the simultaneous algebraic equations A11 minus lambda times K sub 1 plus A12 times K sub 2 plus dot 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 plus A sub 1n times K sub n is equal to 0. The next line would be A21 times K2 plus, and then this one will have your A22 minus lambda times K2 plus dot 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 plus A sub 2n times K sub n equal to 0. It would go on in this manner all the way down until we had a sub n1 times k sub n plus a sub n2 times k2 plus dot 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 plus, and then we would have a n minus lambda times k sub n is equal to 0. Thus, to find a non-trivial solution, x of x prime equal to a times x, we must find a non-trivial vector k that satisfies a minus lambda I times k equals the 0 vector. For this same vector, you'll remember it, right? A minus lambda I times k equal to the 0 vector, to have solutions other than k1 equal to k2 equal to dot 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 equal to kn equal to 0, the determinant of a minus lambda times I has to be equal to 0. This polynomial equation in lambda is called the characteristic equation of the matrix A. Its solutions are the eigenvalues of A. Now, a solution k not equal to the 0 vector of a minus lambda times I times k equal to the 0 vector. Remember, those capital letters are matrices or column vectors corresponding to an eigenvalue. Lambda is called an eigenvector of A. A solution of the homogeneous system A prime equal to A times X is then X equal to K e to the lambda t. So it's really quite amazing and beautiful. So let's take a look at distinct real eigenvalues, so non-repeated eigenvalues. So when the n by n matrix A has n distinct real eigenvalues, lambda 1, lambda 2, all the way down to lambda n, then a set of n linearly independent eigenvectors and those are capital K1, capital K2, all the way down to capital Kn, can always be found, and capital X1 is just going to be capital K times e to the lambda 1t. Capital X2 would be equal to, and this was, K sub 1. And then we'd have K sub 2 e to the lambda 2t. And it would continue in that way until we got to capital X sub n equal to capital K sub n e to the lambda sub n times t. Is a fundamental set, because they're all linearly independent, of solutions of x prime equal to a times x on the interval from minus infinity to infinity. So theorem 8.2.1, general solution, homogeneous systems. Let lambda 1, lambda 2, all the way down to lambda sub n be n distinct real eigenvalues of the coefficient matrix A of the homogeneous system A prime equal to A times x. And let capital K1, capital K2, all the way down to capital Kn be the corresponding eigenvectors. Then the general solution of x prime equal to A times x on the interval minus infinity to infinity is given by x equals C1 times capital K1 e to the lambda 1t plus C2 capital K2 e to the lambda 2t plus plus Cn times capital Kn e to the lambda sub n times t. All right, so first example, let's find the general solution of the given system. So here we go. Well, sometimes it can be useful to, identify what all we've got. So for the first couple times at least we will. A is the coefficient matrix, so that's going to be negative 6, 2 going across, and then second row negative 3, 1. Now we also want to know A minus lambda times I. So that is going to be negative 6 minus lambda, 2, negative 3, and then 1 minus lambda. Cool, cool? Okay, and so now we will be checking out step 1, which is to find the eigenvalues. So to find the eigenvalues, we're going to find the determinant of A minus lambda I, and we're going to set it equal to 0. So determinant A minus lambda times I equal to 0, the scalar 0. Just to note that we're in I2 right here because we have a 2 by 2 matrix, and that's the identity element for matrix multiplication for 2 by 2 matrices. So here we go. We're going to have negative 6 minus lambda 2, then negative 3 and 1 minus lambda. That determinant has to be equal to 0. So then I'm going to factor out the negative from the 6 minus lambda. We'll have 6 plus lambda times 1 minus lambda, so you multiply across and then you subtract the other side. So then minus 2 times negative 3, all of that would be equal to 0. Okay, so let's check this out. We'll have negative 6 minus 6 lambda plus 1 lambda minus lambda squared, and then plus 6 equals 0. And then that will end up giving us what? Positive lambda squared. We will have plus 5 lambda, and then minus 6 plus 6 is 0. The 6 is 0 out, so we'll have lambda times lambda plus 5 is equal to 0. So lambda 1 is 0, and then lambda 2 is negative 5. Cool so far? All right, perfect. Now, second step. We want to find the eigenvectors. So, the general equation is we want to take A minus lambda times I times that k vector is equal to the 0 vector. So this is going to give us vectors. So here we'll check out lambda equal to 0. And if you look at this guy over here, that's what we're going to be working with. So lambda is 0. So we're just going to get our original coefficient matrix. So we're going to end up having -6 minus 0, I'll write it out, 2, -3, 1 minus 0, times the k vector equal to the 0 vector. So then this is just -6, 2, -3, 1 times k1, k2, those are entries in the vector, equal to 0, 0. So if you look at just finding the row reduction, you can form the augmented matrix -6, 2, -3, 1, 0, 0. And then we want to find the reduced row echelon form. So let's go ahead and bring up our calculator, and then we'll go to matrix. And let's see, we'll edit matrix B. Matrix B is going to be 2 by 3. And we have -6, 2, 0 going across, and then -3, 1, 0. You could also solve the system by hand. And then if we quit out of there, and then we go to second matrix math, we're looking for that RREF form, and then we got to name the matrix. It was matrix B, and we end up with 1, -1/3, 0, and 0, 0, 0. So that translates to the system K1 minus 1/3 K2, these are not vector Ks, these are entry Ks, is equal to 0. And so we'll get K1 is equal to 1/3 times K2. So here's kind of a trick that, the author uses, and lots of people, to make it look pretty. If we let K2 equal to 3, then K1 is going to equal to 1. We won't have a fraction. So our vector, eigenvector K1, is equal to 1, 3. Groovy? Okay, so now we've got another one to find. So let's take a look at this other one. This is still part of, did I allow another page? Oh, here we go. I'll just keep going here. So here we go. We will have for lambda 2 equal to -5. So then a minus a minus, minus -5 times I times the k vector. So actually k, capital K2 vector equal to the 0 vector. This one would have been K1 vector. And so putting it together, we'll end up with negative 6, I think it was, and then minus a negative 5 is plus 5. Then we'll have our 2, negative 3, and then 1 plus 5, because minus a minus, times K2, which is just going to be these entries, K1, K2, equal to 0, 0. And then that's going to give us negative 1 to negative 3 and 6. Times K1, K2 equal to 0, 0. So again, putting it in augmented form and using some technology, we'll have this matrix here, and finding that our REF format, let's go back to that same matrix. So second matrices, edit, we're going to edit matrix B, and it's just going to be where we have our eigenvalues. So it'll change to negative 1 in that first entry, and then in that, let's see, row 2, column 2, we'll have 6, and then we're good to go. We'll quit out of there, and then I'm going to do a little trick. If you do second enter, it's entry from last time, and so we'll get a little shortcut to finishing off our reduced row echelon form. All right, so this is going to give us that K1 minus 2, K2 is 0. That means that K1 is 2 times K2. If we let K2 equal to 1, then K1 will be 2. And so our second eigenvector, K2, is going to be 2, 1. Groovy? Okay, so now let's put it together, because at the end of the day, we wanted to find our general solution, right? So, in step 3, general solution. So this is really cool, actually. I think you'll like it. So to find the general solution, you're going to have, just like we had in that theorem, right? Over here, we have K2, K1 and K2. So we just take, our constants and multiply it to K1 and then E times the corresponding eigenvalue. So we're going to have X is equal to C1 and then times K1, which was, where was our K1? 1, 3, times E, that corresponded to the eigenvalue of 0. So this would be E to the 0t, and then plus, K2, with C2 times K2, which was 2, 1. That corresponded to the eigenvalue of negative 5. So at the end of the day, X is going to be C1 times 1, 3, this column vector, plus C, the E term is just 1, plus C2 times the column vector 2, 1, times E to the negative 5t. And we're all done. Isn't that amazing? A real nice way to solve a differential equation, find the general solution to a homogeneous system. All right, so now let's go into phase portrait. I'm not going to get really far into this, but I wanted to touch on it. In the future, I'll be making some corresponding MATLAB videos, I think, to go with this, but so stay tuned. Subscribe, and then you'll get notifications. All right, so writing a solution of a system of linear first-order DEs in terms of matrices is just an alternative to listing the individual functions and the relationships between the constants. So on this one that we just did, we had gotten x was equal to c1 times 1, 3 plus c2 times the vector 2, 1 e to the negative 5t. So this would translate to x at t is equal to c1 plus 2c2 times e to the negative 5t. And then we'd also have y at t would be 3c1 plus c2 e to the negative 5t. And there's some cool apps, where you can see I actually graphed the why isn't this going away? I actually graphed the phase plane for this one, and you can see how all the arrows are going. This is just something I searched for online. There's a lot of different people that have posted this stuff online. So here's that last image. You can do it by hand. It's really kind of tedious. You basically just would go into, one way to do it is to go into parametric mode on your calculator and then just graph a bunch of different graphs like y1 or x1 at t, y1 at t, and you change the values for your constants because they can be any real number. All right, so we can interpret these equations as parametric equations of curves in the xy plane or the phase plane. Each curve corresponding to choices for C1 and C2 is called a trajectory. So each individual one is called, for C1 and C2, is called a trajectory. And then a collection of representative trajectories in the phase plane is called a phase portrait. And so this is what you see here is a phase portrait of the given linear system. The origin is not only a constant solution for x is 0, y is 0 of every 2 by 2 homogeneous linear system, x prime equal to a times x, but is also an important point in the qualitative study of such systems. Cool? I'll be making videos for repeated eigenvalues and for complex eigenvalues in the near future. If you enjoyed the video, please hit that subscribe button and like the video. And I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. Bye.